So we first have to ask ourselves, why do we need to calculate the pressure drop in a packed bed reactor, which is simply a plug flow reactor packed with catalyst particles, and our fluid flows over this packing as it reacts and it is converted into product. So what is the importance of this frictional pressure loss in this packed bed reactor? So we must realize that the only reason why the pressure will drop will be because of friction, not because of reaction or that I might have 2A that forms B and there may be some contraction. This will influence the volumetric flow rate in my bed. The pressure will always drop in my packed bed, so I will have a pressure at the inlet along the length of the reactor. There will be a drop, and that will be due to frictional effects. So why are we interested in these frictional effects? For two reasons. Reason one, we want to calculate the energy requirement of our pumping or our fluid moving equipment. So our reactor needs to operate at a certain pressure, but there will be a drop in that pressure, and this drop in pressure over my reactor is the delta P equipment that forms part of my mechanical energy balance when we have to size our pumping equipment. And of course that determines the kilowatt rating of the motors that we must buy, and in the end, if we have the amount of hours that my reactor operates, that contributes to the operating cost of my system. So that's one reason why it's important, and that is equally true whether I have a liquid or a gas that flows through my reactor. Another reason why it may be important to know which pressure you will be at the outlet of your liquid phase reactor is, let's say you've got operate at the temperature of 500 degrees Celsius and you've got liquid components and you want them to remain in the liquid phase over this entire length of your reactor. If there's a drop in pressure, you must ensure that the pressure at the outlet is still higher than the vapor pressure of your components in that mixture, so that you don't have any gas bubbles forming in your fluid from that system. So our interest is more than just in quantifying the pressure drop and the outlet pressure in our system. We are specifically interested in this part of this subject in gas phase reacting systems. Reason being that if I look at my rate expressions, and now we are always going to work on a mass based, and we use this to denote that we are reminding ourselves that our rate is on a per kilogram catalyst basis, and my rate at which my reactant A disappears will of course be a function of its concentration. And if I think of concentration, it is the molar flow rate in my reactor at any point divided by the volumetric flow rate. And the volumetric flow rate, if I have a gas phase reaction, and we are always going to assume ideal gas behavior, I can calculate this volumetric flow rate using my ideal gas law. Therefore, I need the total amount of molar flow, RT, divided by the pressure at that point in my reactor. And now what happens in my reactor is that pressure, if I either have now a long Z or my independent variable mass, the pressure is decreasing as the fluid flows, and this decrease is due to frictional effects. And as that decreases, this volumetric flow rate is going to increase. So there are different factors that can affect the volumetric flow rate. Of course, what's the reaction stoichiometry? Do I have an exo or an endothermic reaction? So you treated this part, changes in FT in CKN. But now we need to factor in the fact that as the pressure drops, Q is going to go up. And therefore, the concentration of my reactants is going to go down, right? So the pressure, a lower pressure means a lower concentration of reactants, and therefore a lower rate in my reactor at that specific point. In fact, for many catalyzed reacting systems where a gas phase participates in the reaction. The rate is written not in terms of concentration of my reactants, but in terms of their partial pressure. And here it is very easy to see that direct proportionality of my rate to the total pressure, because the partial pressure is simply equal to the mole fraction times the total pressure in my system. So the partial pressure, even if I have no reaction taking place, the partial pressure will drop because the total pressure will go down due to friction. So it's important for us to take note of what happens in my packed bed reactor, what happens to the pressure as a function of different choices that I make as the design engineer. So of course, in CKN, you were able to construct curves of how the flow rate, molar flow rate will change along the length of the reactor, because we had our mole balance for the plug flow reactor that we could simply implement. So now what we also need is an equation that says how does the pressure change with either mass or length or volume of my reactor, how does that change? So we need the equation that describes this slope of this line as I move along the length of my reactor, so that I can integrate that and calculate the pressure at any point to plug into my rate equation. So the equation we will use to give us this slope in terms of the independent variable length in this case is the empirical Ergun equation, and this is the form that you will find it in many of the literature sources, also our textbook, and this is the empirical Ergun equation. Please note, it's empirical, so therefore these constants, the 150 and the 1.75, depends on the fact that you use all the other parameters and variables in SI units. SI units for pressure is Pascal, not kilopascals, Pascal. SI units for any dimension will be meters, so particle diameters, bed diameters must be in meters. The mass flow rate in kilograms per second. Our fluid viscosity, not in centipoise, but in kilograms per meter second. The particle size of my catalyst packing in this bed, so the diameter of these particles that's in my bed, the catalyst particles, of course, influences the pressure drop. You can imagine that if I have a packing made up of baby powder, that the pressure drop will be much steeper. I will have a higher pressure drop than when I have a nice, bigger Ergun size kind of packing in my reactor bed. This G, or mass flux term that appears twice in my Ergun equation, is calculated by taking the mass flow rate in kilograms per second and dividing it by the cross-sectional area of my tube over which I am doing this balance. And of course, this cross-sectional area depends on the diameter of my tubes or tube in my reactor, and that is a variable that the design engineer will have control over. So I can calculate that cross-sectional area in terms of the square of that tube diameter divided by 4. So in fact, we can see that this mass flux is directly proportional to the mass flow rate through that tube and inversely proportional to the square of that tube diameter. So the smaller I make my tube, let's just see whether that makes sense. The smaller I make my tube, the bigger my mass flux will be, and I will have a steeper slope, or the pressure will decrease faster along the length of the reactor, and intuitively, surely that makes sense. So the porosity in the packed bed, that little term over here, is simply calculated by considering the volume that is open, that is available for your fluid to flow through, divided by the total volume in that tube. And please note that epsilon is not a variable that the design engineer has control over. Once you've chosen your catalyst type and the particle size of your catalyst, the way that the catalyst will pack will decide that porosity value. So for a homogeneous single spherical particle diameter catalyst type, that porosity is 0.4. So you will learn more about that in CPA, but the value we are going to assume in this course is 0.4. Important to note, it is not something that you can control or change in order to affect the particle size. It depends on the catalyst type, the particle distribution of your catalyst, and how spherical is it. Is it little particles that can pack like that, etc. Thus far, the entire analysis was the same whether we would consider a liquid or a gas flowing through our reactor. The difference now comes in when we treat this parameter 1 over density. That density refers to the density of my fluid as it flows through my reactor. And so that density I need to know at any position as the fluid flows along the length so that I can determine that slope at each of these points. For a liquid, we are going to assume that the density is not a function of pressure. So we are going to assume incompressible behavior. Therefore, the density in is equal to the density out is equal to the density throughout my reactor, and I can therefore calculate this parameter at the inlet of my reactor and assume that it is a constant when I calculate my pressure drop. For an ideal gas, however, if we recall from CIO how to calculate the density of an ideal gas, we will see that it will change if I change the pressure along the length of my reactor as well as the temperature that we are in fact going to consider in later analysis. Remember, in this calculation, the pressure must be in kilopascals and the temperature must be in Kelvin if the molar mass is in kilograms per kilomole. So just be careful with your units. This must be in pascals. This will be in kilopascals when I calculate the density of an ideal gas. We are now going to derive an algebraic equation that I can use to substitute my gas fluid density as a function of my dependent variables, the total molar flow rate, the temperature, and the pressure along the independent variable that can either be mass, catalyst mass, or the length of the reactor or the reactor volume. So in order to write that 1 over density term in the Ergun equation as a function of the variables that changes along the length or the mass or the volume of my reactor, which may be the total molar flow rate, the temperature, and the pressure, we are going to use our friend, the ideal gas law, together with our steady state realization that mass flow in must still be equal to mass flow out. So we convert that to be in terms of density at the inlet and a volumetric flow rate at the inlet that we will be able to calculate from our given inlet parameters, and then that must always be equal to the density at any point and the volumetric flow rate. If we now make 1 over density the subject of that equation, we can write it in terms of our inlet density, which is something that we will be able to calculate, our inlet volumetric flow rate, and our volumetric flow rate that will change, and that will change because I change temperature, the number of moles, because I have a reacting system, and because of the change in pressure in my system. So substitution leads me to this group of terms. So I can now substitute that. So let's just remind ourselves that this over here, that whole group of terms is actually now 1 over my density. And what happened here is that I for now assumed that my temperature over T0, inlet temperature, is equal to 1 because we are still going to assume isothermal reactor behavior just for now. Note that Vogler and many older literature available online describes this change in the molar flow rate along the length of the reactor in terms of an epsilon, which is an expansion factor, multiplied by the conversion of a single reactant in your system. Of course, this limits the application of this equation to a system where I only have one single reaction that takes place. They use that because it allows for analytical solution of this differential equation. We are not going to tie our hands in this manner because we have got ODE end and we've got solve IVP, and we are all now very comfortable in Python in order to solve them numerically. So we are not going to take the expansion factor approach and this analytical solution of the differential equations.